Okay, okay. Then let's start. Okay, so the theme of this particular month is cleaning robots, as we have been discussing about it, and we conducted already two sessions on it. And today the theme would be navigation for wheeled mobile robots. And the goal would be that we would be targeting it with respect to Roombas or cleaning robots, because this is what we did last time. So last time what we did was we deconstructed Roomba, we did reverse engineering of Roomba, and we understood all the components that a Roomba system has and how it might work. And today we will go into one particular aspect of Roomba mobile robots, and that is navigation, because navigation is a very important part for cleaning robots. And this is what we will be targeting today, and we will be targeting navigation on a general basis, but also taking Roomba into account. And that means we will be only talking about wheeled mobile robots and not aerial mobile robots or underwater um, autonomous vehicles. And we'll talk first about navigation, and then we'll talk about autonomous navigation and different approaches that we have for that. So the agenda for today is, after this introductory presentation, I'll define the problem for today, and we'll do a brainstorming, and we'll have some discussion, in-depth discussion about it. And after that, we'll have introductions and casual networking. So the goal would be that we'll be collaboratively trying to solve this problem. And so uh, feel free to give your suggestions along the way. So let's start. And before I define the problem, I want to also let you know that today we are doing it a bit differently. So it's not on PowerPoint, it's on a different application called Miro Board. And the idea is that this app allows us to collaboratively solve problems or brainstorm, essentially. And the idea is that we'll be making mind maps, and we'll be collecting ideas on solving the problem for today. And for that, uh, for those of you who want to contribute, and you want to also edit it and access to it along with me, feel free to give me your email ID, and I'll quickly add you to it. So I think Apuru already has. And let's see how many of you want to collaborate. You can just give me your email ID, just message me on Discord or write on the chat room. Mudit, do you want to collaborate? Okay, okay. And Apurva and better than yesterday. So, do you want to collaborate, or do you want to just listen? That's also fine. Okay, so in that case, you can give me your email ID. Okay. Okay, all right. Then I think we can continue with it. So, Apurv, you also have access now, right? Okay, okay. Yeah, meanwhile, I'm continuing defining the problem. You can check whether you have access or not. Okay. Okay, so the task is such that since we are talking about cleaning robots, so we are going to assume that we have a Roomba here, and the goal is that it covers the whole of this house. So this is a layout of a house, and these could be, classified as separate rooms or portions of the house. And the idea is that it should actually cover as much portion as possible and clean it. So that is the entire premise of the problem. And the way that we would be discussing it is we would first try to understand what navigation is. So instead of the Roomba, if for example you were to do a task such that you have to go to the entire room and every single portion and clean it, how would you be doing it? So let's talk about navigation problem in general. So so basically, to clean the room, and here's where you can write if you want to as well your suggestion. So the task is to clean the house covering maximum area, covering actually the entire area. So so this is actually the goal, and to accomplish this goal we need to have the ability to actually navigate through the environment. And now in this slide we are talking about just humans, essentially. So how would a human being try to navigate? What do we actually consider when we are trying to go through the room? What are the things that we need? Anyone wants to add something here? So to navigate the whole room, what are the essential? What are the things that you consider essentially when you are going to navigate through the whole room? Hmm. So sensing the environment, or I'll just write sensing. What else? And we also have to take the goal into account. Sorry, obstacle detection. Obstacle detection. Also, feel free to write here as well if you have the access. Okay, another thing. Ah, okay, okay. No worries. So, by the way, we are doing it a bit collaboratively today. So, if you also want to get access to this, you can write your email ID and I'll provide you access to this Miro board. Or you can just like say and I'll draw it. Path planning. Let me see why this is okay. Path planning. And I think, like, actually if we divide it into uh, if we actually divide navigation into categories, then it would be just localization, and inside this localization we can have different things. So localization would be one thing, and then generating a map of the environment. Mapping, and inside this I think for to generate this map we need to have sensing, right? And we need to have obstacle avoidance as well. For to generate the map, and this localization is basically knowing the robot trying to know its own location, or in our case humans, we are like how do we know our position? That is the thing. Free space, so wouldn't this, like, what do you mean, for path planning or what? Mm-hmm. Yeah. Mm-hmm. But I think it would come in the same category as obstacle detection, like because I mean, yeah, just leave it written, because this is we can keep it that way. Okay, and then there's this reaching goal, and to I think taking goal into account, the path planning would come under this category. Also, correct me if something is not correct as well. Uh, so the task is actually to clean the robot, like so the task problem is defined such that we have a Roomba, and the goal is that it has to clean the whole room, and for that we are tackling the navigation problem. And here we are talking about navigation in general, what is required if we as a human were to navigate through the whole room to clean. Yeah, so like for example, for path planning, there could be small sets of goals. I think for one particular case, and but the like the overall goal is just to cover the whole space. Yeah, maybe the category is like not ideally defined. What are your suggestions? Okay, I actually defined it in a separate category. So Miro is actually a bit weird. Let me see. Yeah, so I actually defined it like this. Yeah, so it goes back there. Yeah, I think drawing with the hand would have been better. This is super weird. Okay, anyway, yeah, we get the point. All right. Yeah. So what else? What else do we consider when exploring an environment for a goal? Yeah. So storing environment details, probably something. I guess I'll switch to writing with hand from next slide, because this is not as Mhm. So yeah, yeah, yeah. It makes sense. So I changed it to object detection, and I think we didn't write much options in localization. So here we can probably write something. What are different ways of localization? Now this is not considering autonomous vehicles or anything into account. Just general what we would be probably how do we know our location. So so okay. Hmm. Mm. Hmm. Yeah, it has wheel encoders as well. Yeah, yeah, it has. Yeah, exactly. Yeah, yeah, yeah. So like there are. Yeah, and actually also for visual slam, they just uh, use mostly image based and not depth data. So, like, coming back to navigation as a whole, like, if there's a human now, we know that it needs to know find a way to figure out the map of the surrounding that it wants to have, and for that it needs to have object detection, so walls, and maybe there are tables, chairs, and all these things, and it has to sense, it has to have senses like we humans have: eyes, ears, nose, and it needs to. I think free space is, again, I think it would be part of probably like sensing or something, right? So, but it's okay, let it be there. And then localization is knowing the human, so we know where we are with respect to the environment, so this is important as well. And then we have to keep our goal in mind, that the goal is to clean the whole of room, and for that we have to be deciding which area we should cover first, and which and how are the smaller paths that we would be generating, so that ultimately the whole thing is solved. And now talking about autonomous navigation. So for autonomous navigation, the goal is that we have a robot. The idea is that we have a robot, and the robot essentially autonomously navigates. So the robot would do it on its own without any human intervention, and that's what Roombas are doing, right? So with autonomous navigation, the concept of localization, mapping, and reaching goal, the robot has to find a way to figure this out on its own, and this is what we will be discussing today. How can the robot learn to localize itself in an environment? How can the robot know a map of the environment? So now here again, I'll share a few things about autonomous navigation considering this particular problem. So for autonomous navigation, we have two approaches. One is a heuristic approach, and the other is, just a minute, and the other is optimal approach. So by heuristic approach, we are basically defining a set of rules that the robot follows, regardless of what the environment is. Define set of rules, and this is a simpler way of going about it. So let's see how this could be used in our case. So in our case, the goal is simply to clean this whole thing. So we could just define a simple rule that the robot always goes, in the front, and whenever there is some a collision with some walls or some obstacle, then maybe it for example rotates to a specific position. So now maybe the robot is somewhere like this, and it collides here, and then we define a pre-defined angle that on all collisions it just diverts to a specific locations. And so the idea is that we are hoping that after a lot of steps, it would kind of you know uh, cover the whole of the environment by colliding with different walls, but it would not be optimal. So this is the heuristic approach. It would kind of cover the whole room. Maybe it takes a lot of time and it's not very efficient, but this is one particular approach of autonomous navigation, and we are ignoring the environment. We are not caring about its own location and mapping. So this is a very simple way of going about it. And one example of this, sorry, under heuristic approach. No, no, no. I don't think so. I mean, they are using computer vision, and I don't know the exact approach that they have, but they are using computer vision, and they are doing object detection and everything. So they are perceiving the environment, and they are doing planning and everything. So this is a very simplistic approach to just give you an idea that this is also under this category, that even if it just does a predefined action, it's possible to uh, do this task, and we can call it that it's doing it autonomously, right? It's without human intervention. Yeah, exactly, exactly. So, but this is, of course, not ideal because we are looking for an optimal approach that can do this, that can maybe cover the whole of the room area in the minimum possible uh, time, or whatever the criteria for optimization was. So, if this is an empty room, we want it to, you know, not go randomly around it and hopefully trying to clean the whole room, but rather we want it to follow the optimal path. So let's say maybe it's going like this, and it's covering the whole of room or something like that. Yeah, so with optimal approach, basically we can have multiple categories. Again, one would be when, so when we are thinking of autonomous navigation, we would crudely just think of localization and mapping for now, and also after we have we are localizing it, we would care about path planning. So let's just consider these three aspects today. So the categories would essentially be, for optimal approach, if we have if we care only about localization, and, and no uh, and map is given. So this is one type of approach, and other is if we care about localization and map is also unknown. So these are two things that we consider here, and here we know that like we don't care about no localization, and also no mapping. So this is how we can like define this thing. And now coming to localization, and let's see, we have the map is given to us. So if the map is given to us, so we know that where we know where the walls are, and it's an empty space, empty room, empty house that we are considering here. So uh, with the with this approach of the map being given, we can use something called particle filters. And the idea behind particle filters is that it slowly learns its a robot's localization position, and accurately determines it slowly over time uh, by going around the room. So mostly we are trying to figure out the localized position of it. So initially, so let's say we don't know where the robot is. Let's remove this robot from here. So we don't know where the robot is. Sorry, the robot doesn't know where it is, but let's say ideally that the robot is located. Let's say it's facing here at a corner. Just I just taking a random example, and we know that from our previous session, we know that Roomba is equipped with a lidar as well here, and it also has camera. So here is, let's say we have a lidar, and this lidar now gives us this reading. So to point out again, what the robot sees is just this. Now the robot has this reading, right? So this is front facing. The robot just sees this, and it knows the whole map, but it doesn't know exactly where it is. We have to find where it is, because it could actually be anywhere, right? The robot just knows this, and this means that it could even be here. Let me draw this with a different. It could very much be here, right? And this, if this is the lidar reading, it could be in any of the corners, because the lidar reading would be similar, right? So we have multiple options that we can consider, but initially what we do is we give we just give random initializations uniformly throughout the whole map. We could say that robot could be in this position with this particular orientation, or it could be in this position with this orientation. We just give it randomly, let's say 50 or 100, or any number of particles, and this is what we mean by particles here. So we just denote several possibilities, and the idea is that over time these number of possibilities would decrease. So now it's equally, initially it's equally likely that it can be actually anywhere, but now if we take this into account, then we update this probabilities also. Like, feel free to stop me here if something is unclear, or you want to add something. So it's clear till now that what we are doing, to repeat, is that we are trying to the robot is trying to know its location, and it doesn't know. All it knows is that there is this lidar reading that it has, and it knows the map somehow. Yeah. Anyone wants to say something, or should I continue? Continue, right? Or what did you say? Ah, okay. Yeah. So initially, it's equally likely to be it at any of these random positions. But if we take this reading into account now, this lidar readings, then at any of these positions now, this lidar reading is also different for each of these positions, and so matching these positions, matching these lidar readings with our actual reading, we can increase the probability. So now how I'll show that the probability is high is, maybe I'll use let's use a highlighter. So yeah, so this highlight is how I'll show great probability. So this probability, this area is more. This means the probability is high at this particular location. Also, at this it's high, but at other locations maybe it's not that high, because the lidar readings are also not matching, right? So this is also high. So all these probabilities are low, and based on this, now we have a new probability distribution. And what we do in particle filters is, now we draw another set of samples. So I'll now remove all of these things, and now based on the probability distribution, the where the probability is high, we get more samples, and where probability is low, the intermediate particles, we draw less samples. So now this is what I'm doing. Now what I'm doing is I'm drawing new samples. So these are new samples. So there's a so it just draws more samples around these areas, maybe few here, because there's some probability here as well. But more samples are being drawn at higher probabilities. So this is how we kind of how the new distribution would be. So I've just taken three here. There could be more depending upon the number of particles. So this is now the new set of particles. Now again, it would take. Now what it would do is it would the robot would maybe move to a new position, and it would, let's draw it with what it would do is the robot would okay, it's the same color again. Yeah. The robot would move to a new location, and it would have a new lidar reading, and we again do the same thing. So we move all of these particles as well, and we then, let's say, move this particle to a new location, this particle to a new location, all these particles the same amount we would be moving, and we would then again compare the lidar reading, match, and draw new samples. And this way we would be repeating it till we would be probably left with just this particular location with a very high probability, and all other locations would be low probability. So to summarize, let me write a few steps, because I think it can get complicated. So initial step is actually, okay, so we what let me write what we know. So we have a known map. We know we have a lidar. We have lidar readings, let's say, and based on these, what it does is basically it assign it draws not draws makes particles, let's say 50 particles of equal probability of being in that particular position. So initially it could be in any of those positions, and then after that, based on the radar readings, probability or weights is also how we define it. Probability is updated, right? So initially we updated these probability values, and then what we do again is then we draw new samples, samples based on new probability distributions. And once we draw the new samples, and then what we do is then we again compare the lidar readings with original, and we update the probabilities. Then the robot moves, and we keep kind of repeating it. So I hope this gives a vague sense. Although what I would recommend is, maybe my explanation is not as clear. What I would recommend is that you guys also watch this series by MATLAB, the autonomous navigation series. So I think this has really good explanation. So this you can watch after this. But if you have doubts, let me know right now. Aditi, was it clear or totally not clear? Yeah. 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 So. Mhm. Yeah, yeah, exactly. Yeah, that is the idea. And I just want to give like an overview of what this is doing. So this would be applicable when we have a map, because we are kind of in a way. Yeah, exactly. Yes, exactly. So without the map, it would be really this method would not be applicable. So in that case, we would go for a different method. So the only thing to remember from this is that we are this is applicable when we have a map and we are trying to localize it by taking the lidar readings into account, and also then updating the probability of distribution of different particles that we assume it could be. So initially we are really uncertain where it could be. It could be anywhere, right? So that's why we have so many particles randomly uniformly located throughout the whole house. But then we saw that okay, now there are more particles around this, because there's probably the probability is high because the lidar location matches. And then so on, as it moves, we get more information based on the lidar readings, and we refine it till after some point it becomes really accurate. Now this is all theory. Has anyone used particle filters and can suggest some maps? Because I haven't used it before, uh, this particular approach. So maybe let's have a discussion about practical implementation of it, if anyone has used it before or has some idea about it. Okay, everyone is muted means probably not. Okay. Okay, so I think this would also be interesting. Maybe we can, share some links on the Discord server on how this can be used with ROS for mobile robots, with Turtlebot or something, which packages are good, which are not. So I think that would be interesting. And now the other case where we have where the map is also unknown. So here in this particular case, in the particle filter approach, what the robot just, let me draw it in a new slide. Yeah. So in the particle filter approach, this is what the robot actually sees, right? The lidar reading, if it is a corner, that something like this, and it knows the map is fed to it as well. So it so the map. So this particular map that we this particular map. Sorry. Yeah, this particular map that we do, this is what the robot kind of knows, right? But in a slam approach, where we have where we don't know the map, so the robot doesn't know anything, and the robot doesn't know where it is, and the robot does has no idea about map. So that's when we use this approach called slam. And here we can talk about multiple approaches. I think you guys are more familiar with slam, so feel free to add more approaches. I can probably share one or two approaches that I know. So slam is simultaneous localization and mapping. and mapping, because we don't know the localized position and we don't know the map, and this is sometimes called a chicken and egg problem, because to get some location, to get some localized position, we need map, right? We need some information about the map, like for particle filters we knew the map so we could localize it, but at the same time to get the map, maybe we need localize some information about localization as well. So like these localization and mapping, they are interdependent, so that's why this is called a chicken and egg problem. So how do we approach it? Let's imagine an ideal scenario where we have all the perfect sensors. So let's keep the same environment. So this is our environment. Now what it does is, basically we know that it has odometry, and odometry is basically the we know from our last session also that to repeat that Roomba has three wheels. So this is a caster wheel, and this is not actuated, and these two wheels have motors, and they also have encoders. And this encoder is basically used to find the position of the robot based on the wheel movement. So this can be directly be used to determine. Now how is it used to determine the robot's position? So let's say the robot moved from here to here, so we know from the number of wheel rotations that it the distance that it traveled, and also the orientations based on the movement of each of the wheels. So let's imagine in an ideal world that these sensors are really perfect. So we really know what the change of location would be, what the new location would be. So initially, let's start actually with a corner to give an idea about how this might work. So initially, maybe the robot is facing the corner, something like this, and there's this lidar reading. So initially this is where it is, and maybe now the robot rotates and turns to moves to this new position, and also rotates a bit. So this would be the new lidar. Oops. This would be the new lidar reading, right? So the good part about an ideal system is that we know the robot was here initially, and we know the lidar readings, and we also assume that this is perfect, because this would also actually in actual situation not be perfect. There could be errors like in lidar readings we do have, but let's assume there's this ideal situation, and this is perfect indicator of the corner. And after some time we know that it moves this much distance, so we now accurately know the position at this point as well, with respect to the initial point, and we know this as well. So you can imagine how simple this is in this particular case, because all it needs to do is it just needs to go around and explore the environment. So in a new location here, it would have new, and it knows its particular localized position as well, and also that of environment. So all it needs to do is just go around and cover the whole environment, and it can easily navigate through the environment. But we know that in a real scenario, neither the odometry is perfect, nor the lidar readings. So the lidar readings would look something like this maybe, and the odometry reading is also not perfect. Maybe there are some encoders that are some one of the encoders or maybe both are not giving accurate reading. So after this particular movement, what it does is maybe the ideal location is this, but what the odometry maybe gives is probably something like this, right? I mean, you can imagine that this level of error could arise there. So maybe it gives like this, and also then what the lidar would give would probably be something like this, right? Because because the actual location is like this, so it would still show the wall, but it's rotated like this, so the robot would assume that it's in this position and not in the actual position. Does it make sense? Does anyone want to add or ask something? No, I mean, be honest. Is it is it clear, or do you need some explanations? Because it can get okay, okay. Okay, yeah, thanks for the feedback. Yeah, so what happens is like after this, this is the new location, and we see that after a while, the ideal location maybe it goes again to this particular corner. Now it goes to this particular uh, corner, and we have this reading now. But again, this error is I think called drift, but I might be wrong with the terminology here. So after this, now this particular drift or error is accumulated. So the new location that the robot thinks it where it is it might think it is here. Because the odometry reading is faulty, and then but actually it is here, so the lidar reading would be still corners, but it would be something like this. So you can imagine based on this. Now if I draw more, I guess it would become really messy on this, but I think it gives the idea. Now the idea with the visual slam is that once this particular robot navigates enough, and maybe after some time it reaches to the original position again, and maybe now the original position is something like this, but the lidar reading is kind of matching the original, matching the original position. And so what the agent realizes after some time is that this particular position and these are actually the same. So the idea is after some time it reaches to this original position, but the odometry reading gives us wrong estimate of its location. So what it does is it realizes this is the same, and so it makes an adjustment. So this particular thing would be it makes an adjustment to its location, such that now this particular thing is actually here. So the probability now it becomes really certain once it comes back to the original position, and this is called loop closure. Once it comes back to the original position, its confidence level increases that okay, this is actually in this position and not this. And so what it does, it backtracks to the robot's position, such that all the other older probabilities also get updated. And when that happens, it now updates the older locations as well, and it kind of now gives us a good map. Now I'll just erase everything and draw how the map would look like, and that would probably connect everything back together and give uh, clear indicator of it. No, yeah, yeah. So, so this is our ideal map. The robot doesn't know that this is the ideal map. What the robot sees is, as we saw that initially it sees that okay, this is here. Now we are not taking the ideal sensors scenario into account. Now when the robot is here, it sees this. When the robot is here, it actually sees something like this. Depends on upon the inaccuracy that we have. And when it is actually here, then it gives something like this. Or yeah, you get the idea. So this would be totally inaccurate. So maybe something like this representing this particular corner, and so this will be all over the place. Now you can imagine this is not a good map, right? This is broken and this is not an accurate indicator. So once the robot goes back to the original position, it updates it. So let me draw one more. So the last map, once it goes back to the actual original position, the robot thinks it is here, and so it might give this particular thing. And the robot realizes that this is the same position based on the lidar reading, and so it just updates its position odometry position. And now this is how the updated position would look like, because all the intermediate ones would be updated as well. So this would be the updated position, and the new one and it started with the when it came back to it, because this is how it is knowing that it is this position, and it updates the confidence level of all older positions. um, yeah, this is basically slam. I think this approach is the post graph estimation approach, or post graph approach of slam. And then it could actually use a different sensor instead of lidar. When it uses an image based approach, then it is called visual slam actually. So this is also pretty cool. So should I talk briefly about visual slam, or do you want to have you want to talk more about this, or you have any doubts about this? Okay. Yeah. So I'm again like not going super deep into any of these things, just giving you a brief idea. Uh, because visual slam concept is actually pretty cool. So so the idea is now again the robot here, the damn it. uh, this is the robot here, and it this is, let's say, this is one portion of a map. The visual slam approach is it's kind of same, but with a visuals with the computer vision approach. So using image data, so what it does is now here it captures images, right? So it maybe takes up an image here, and the image might look something like maybe something like this, because this is representing the corner, right? This is one image that is captured, and then it would go it would rotate and move to the next position. The next position is this, and it captures image here. Now here the image is here. The image is just this wall. So the idea with visual slam is that it kind of tries to find correspondences between different images. Now you can see how this would be a big problem when we have just plain walls, right? And that's where a major disadvantage of visual slam lies. So it does not work where we do not have features. So because there would be no key points to match. So now let's imagine that there are different kinds of textures on the wall. So the wall is maybe some portion of it is, I don't know, there's some texture or something, and in this particular portion uh, we have this texture. So actually this position is quite far. What happens in visual slam is just it would take the next immediate movement. So let's draw it with dotted line or something, and you can see that the image would be quite similar to the previous one. It would be pretty close but slightly different. So we are assuming that we have textures like these on the wall. So this is, let's say that this is image 1 and this is image 2, right? And this is again like image 1 and this is image 2. So image 2, you can imagine now that it would be slightly different. Maybe now the wall position is slightly here and the textures would still be there, but slightly different. So let's say we have three strands of these here are captured. So what is what the visual slam approach is that it finds these key points. Let's say for simplicity that the key point is just let's just take this particular edge as a key point. There can the key points are basically features that we use to match in different images. So mm okay, let's just say that this wall, this edge is a feature. What it does is it matches these particular things, and now I have to use another slide. Okay, this is the robot. This is the corner. This is the robot at another position. This is image 1 and this is image 2. So I'll draw these images, let's say separately, two different images now in 3D. And this is, let's say, the Roomba, the camera. Let's just say that the camera lies somewhere here. So this is for position 1 of the Roomba, position 2 of the Roomba, and so this is 1 2, and then this is again image 1 and image 2, right? Okay. Now we saw that we have these features here. So this and let's say this and this and this. So we have these features here. The visual slam approach is crudely speaking that it finds these key points. So let's say these are several key points, and these are the positions. So basically it does a sort of a triangulation, and it not like this. So this is the camera. This is position one of the camera. We just draw a line from here, and uh, from camera to. I mean, for simplicity, I think I can draw it probably around here because I'm trying to find an intersection. So what it would do is it would find a corresponding key point, and for that we use these feature detector feature detector approaches like this sift surf, all these things that we also had in one of the computer vision sections previously. So these key point detection approaches, so it finds whether it's a point, or whichever key point it is, and then we what we do is just uh, we know the camera positions, and we kind of make projections onto it, and the idea is that we kind of find a 3D point corresponding to these two image points. So these two image points corresponds to this one 3D point, and this another the other two image points might correspond to this new point, and you can imagine like how this would build a 3D model somehow, because what we are doing is just triangulation. So two 2D points in two planes, and then these these are two intersections from the camera origin centers, and we just do an intersection, and we find the intersecting points and several of these points, and so this would give us these several points that would make up this wall. So this kind of a 3D wall, not as accurate, it would just be points like these. So this is how it generates maps basically. And now about localization. uh, so it uses this map approach to again refine its own localized position. So as it goes through, as the robot goes through, yeah. Mhm. The particle filter one. Yeah. The pose graph, the other slam approach, right? Mhm. Yeah, 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 exactly. Hmm. It doesn't know till it till the loop closes, till it realizes that there is a till it actually comes back to the original position, and based on the lidar information, it realizes that this is exactly where we were when we started. And so what it does, it makes adjustments to the odometry, so it kind of understands uh, what error in odometry might have been, and it updates all of the previous locations. I think there can be a better image in Google. uh, Pose graph slam. This maybe, no. Okay, slam loop closure. I think this might give. Yeah, so here you can see like I think this also is not what I want to show, but this is like what I was trying to show you that maybe the room is actually perfectly rectangle, right? But actually it because of odometry readings it kind of goes up to here. The This is not correctly estimated, and so after the end position it does is it updates this particular position, and after that all of the intermediate um poses are updated such that the map is also now a more accurate indicator. Let me see if there's a better. Not in each position, just at this when it reaches to the final position towards the end. Yeah, loop closure collection. Yeah, yeah, exactly. The previous ones would be updated as well. Actually, there's a really good diagram. I think it is was in one of my lectures, so I can't find it right now. But I think like the goal of this session is not to give you super deep because the information, because that's not possible, right? There's lots of math underlying it as well. But at least now when you read it, when you read a paper or something, you would get really good. You would learn really quickly because these things take some time to get an intuitive understanding of. So okay, yeah. So moving back to visual slam, I forgot what exactly I was trying to do. Yeah. Okay. So like we saw that how it makes. Yeah. So I think I finished this and now I was going to draw again. Do you have anything to add to this? Okay. Okay, okay. Yeah. Yeah, so now moving to this particular thing, our Roomba. Uh, let's go to our goal now. So our goal is coming back to our goal. Our goal is to cover most of the area, all of the area actually of our environment, and there's a vacuum attached to it, so it just cleans everywhere it goes if it is turned on. And so you can now imagine that how we can use different approaches. So for the case when we are given the map, we could use a localization, the particle filter localization type approach to slowly update where this is with respect to the environment, so the robot knows that okay, it is, let's say, here now, right? And it then decides the next goal that it has to go, and it can now find a path and it can go there. So the next step would be path planning after we have a map. And another for the slam approach also, you can now imagine that all we are doing with these approaches is we are trying to find the localized position of the robot with respect to the environment and understand the environment more clearly. Now, these things are like straightforward on theory, but you can imagine that if there are moving obstacles, this approach would be really bad. So slam would also not be very accurate. So I imagine I remember actually like when I was implementing visual slam. So when there were like people moving around, the map was really messed up because let's say there is a person around here, and like it captures the image here, and the person would move around here after some time. So you can imagine like it would create a really weird map with the person maybe at multiple places, and maybe the correspondences are also wrong. So I think for Visual Slam, at least what I have used is that it needs to have the environment as static as possible. So that's a limitation, and also it needs to have these features because it's dependent on these features. So this is one limitation of Visual Slam. um, and you can use other this Kalman filter based slams as well. I think that is more complicated to explain in just today's session, so we'll not go into it. But moving on to path planning, I'll just give a brief idea. What we are doing is basically you might have heard of these A star algorithms, these iterative deepening methodologies, breadth first search, depth first search. So all these things come under a way of doing path planning. So once we know the environment, what it the goal is that it has to maybe find smaller goals. And also correct me on this because it didn't review path planning for today's session much. So let's say like initially it defines one particular goal up to a certain distance, and then it updates the goal and goes to a new distance, and finds these trajectories or paths in between. So let me draw a bit more clearly. Just rub it. Right. So just on this portion, so this is let's say one goal, and what we have a robot here. It generates a plan here, and also avoiding obstacles that might come, the dynamic obstacles and so on. And after this point it just goes to a new point, and it just defines a path again, and so on, till it actually covers the whole of room. I think that's how the basically the whole concept of Roomba is. And since it knows the map, it knows that it can cover the whole room by doing these multiple path plannings, and it kind of tries to find the optimal paths. So there could be like multiple paths. So it uses these algorithms. I'll not go into detail in today's talk. And it kind of tries to find an optimal path for each of the goal. Yeah, does anyone want to add something? So this is all that I have to share for navigation. Let's now talk about what you guys have to say about it, and if you have any suggestions or anything you want to add, or even in path planning if you want to say something. Okay, so over to you guys now. So I think they can be implemented on ROS. There could be you could also just have a like MATLAB code, or maybe write a Python script or something if you want to do it from scratch and understand it more deeply. But ROS has already packages for these SLAM, RTAB map someone mentioned today, and G mapping, all these different packages. So you use these you just use these packages, so you don't write the code. You just kind of link the camera output, the odometry data, and whatever you need with the package. And uh, and uh, the slam part is what the package does, because the implementation is already there. So So actually, yeah, I think processing is really important. What I used Slam on was for I used it on this particular drone, and it is equipped with this real sense camera. So this camera is doing the visual slam, and it has this. The processor was like not very. It was very old, and I can check the specs. I don't remember exactly, but I was having trouble with visual slam because of this really small processor, because this drone is not designed for that. Sorry. No, 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 it's not. It was using some Intel older Atom processor or something. And I think, by the way, it's out of production now. It was not that advanced of a. The main purpose of it was actually it's an educational robot, I think. So you saw here Raspberry Pi, right? No, I think the processor is different. It's in Intel processor here. Specifications.